All right, welcome to the second video of 1.2 featuring October. You are seeing October in her non-regular state of being calm. This is not how she normally is. Don't be fooled. She's eating on my bookcase. Okay, so this first video, pretty hard. It was hard when I took this class all those many years ago, and it's going to be hard when you take this class too. And that's okay, because that section, that video, is not this whole class. And in fact, it's not even this whole section. This video will probably also be pretty long, but it will not be as bad as the first video. And the video after that will be shorter and not as bad as this video, okay? So take deep breaths, calm down, do what you can, learn what you can, ask questions, and then move on. Okay, don't get bogged down too much in this. This stuff gets basically every calculus student. Okay, we got to get through it. We got to talk about it. We'll reference it later. But you honestly, you'll be okay if you have 0% understanding of that last video. You'll still probably be okay in this class. But try for sure. I don't want you to lose all hope just because it's difficult, because it is difficult. I barely understood it as a student myself. Okay, so let's get into the second video. Example 3. Evaluate the integral from 3 to 6 of the square root of 9 minus x minus 3 squared dx. Now, you might be panicking. You might be saying, Jason, what are you talking about? This is impossible. How am I supposed to do this? Doesn't this look terrible? And in fact, later on in the class, we're going to figure out another way of doing this, and it's going to be kind of terrible. And I'm going to say, remember the second section of the class. This problem is easy. That's my claim. This problem is easy. And you might be saying, Jason, you're crazy. You do too much math. Of course it's easy for you. No. This problem is not that bad for you either. The hint is in the section title. Integrals as area. Remember, the definite integral is just the area under the curve. Well, this is our function. What does this function look like? This function looks like y equals the square root of 9 minus x minus 3 squared. Okay, that's not really helpful, Jason. Let me move things around for you. You're going to see this a lot. So this pattern is really going to come into play a lot in this section. Let's square both sides. If two things are equal, then if you square them, they're still equal. Although the converse isn't always true. Square both sides, we're going to cancel the square root. We get 9 minus x minus 3 squared. And now let's add this to both sides. That's going to give us x minus 3 squared plus y squared equals 9. Do you see it yet? Feel free to pause the video if you want to take some time to ruminate. You may or may not be familiar with this. But after this section, you will be expected to be familiar with this, but it's fine if you aren't now. This is a circle. This is the equation of a circle. Well, if a definite integral is just area, and this is just a circle, do you know the area of a circle? I bet all of you do. And if you don't, you can Google the formula and you can use it. That's what I meant when I said it's easy. It looks really messy, but at its heart, it's just the area of a circle. And specifically, this is a circle with center. Of 3, 0. Remember, this means it's shifted right 3 units. And radius of 3. So let's graph our function. Now, they're not entirely the same, right? These two things are not entirely the same. On the top, it's only positive values, right? There's no plus or minus in the square root. Only positive values, where on the bottom, y can be negative as well. So they're not exactly the same. It's not a full circle, actually a semicircle. Okay. So this right here is the top part of semicircle. But still useful. So the center is at 0, 3. And the radius is 3. So this is one side. The other side is going to be at 6. And the radius is 3, upper half of a semicircle. So this is 3, right? This is 3. Semicircle, we're just looking at the area. Well, you can find that. What's the area of a circle? Well, the area of a semicircle will just be half of that. So that's all we have to do. Area of a circle is just pi times the radius squared. And we just want a semicircle. So just cut that area in half. Plug in 3 and you're done. This integral is just 9/2 pi, or 9 pi over 2. Right? The radius is 3. 3 squared is 9. No calculus necessary. When I said it's easy, you have to remember some geometry. You have to remember some algebra. But definite integrals are just area. So in this video, we're just going to be graphing things and then calculating areas like you've been doing for however many years in school. Well, you're still in school, I guess. But yeah, just integral. Integrals, area. Definite integral is the limit of Riemann sums. Infinitely many rectangles gives us that area. But sometimes we don't need to draw rectangles at all. Sometimes we already know the area. Sometimes you'll have trapezoids, you'll have rectangles, you'll have triangles. We know area formulas for all of those. So that's what we're doing in this video, which should hopefully be a little bit more achievable. But not achievable. It's all achievable. It's easier, okay? We're just going to say that. Not as bad, but all important. Definition. Here, I want to talk about the difference between total area and net signed area. So let's say we're looking at a function from like 0 to 3. And say the function looks like this. This is 3. This is 2. This is 1. Well, there's really 3 areas. We can look at this area under the curve. We can look at this area over the curve. Sorry, yeah, over the curve. And we can look at this area under the curve. So now you might already know where I'm going with this. Total area versus net signed area. But let's formally introduce it. Okay. The total area, A, is going to be just this first area plus the second area plus the third area. We don't really deal with negative area usually. When I ask, what is the area of this thing? Usually we don't deal in concepts of negatives. So we'll just add up all of the areas to get the total area. Okay. Now, this is going to manifest itself, this total area is going to manifest itself in a couple different ways. This is going to come up a lot of times when we talk about the relationship between speed and total distance traveled. Remember, there's a difference between speed and velocity. Speed is always positive. Speed is what your speedometer says. You're going in reverse in your car, your speedometer is not going negative, okay? So, and then that'll be useful when we talk about distance traveled, where even if I drive in a circle, yes, I still travel distance, even if I'm back where I started. There's no sign, there's no negatives here. And in terms of definite integrals, what we relate these areas to is the integral Our limits of integration here are 0 to 3 of whatever our function is, but we're taking the absolute value of the function. So total area is the definite integral of absolute value of the function. We're looking at total area. We're forcing everything to be positive, even though the function's negative down here. We're forcing it to be positive. So if you want, we can think of the absolute value. It's going to look like this. Finding the area under this red curve. That's the total area. All right, and then let's contrast this with net signed area, which I think you probably know where I'm going at this point. That's going to, nice line, Jason. I'll call that, it doesn't matter what I call it. I'll call it A star here. And that's going to be the positive area, heavy quotes, minus the negative area. So if it's under the x-axis, we'll count it as negative. If it's above the x-axis, we'll call it positive. And this is what's actually happening when we directly take an integral. We say integrals are area under the curve, and that's really true for positive curves. But when we get into negative curves, the relationship between area and integral is a little fuzzier. So an integral, a definite integral, is the net signed area, not actually the total area, unless we force it to be positive with absolute values. That's why in the first video, we made some assumptions about non-negativity. Okay, and if this total area is speed and distance traveled, well, what's the analog, the correlation? What's the other attached part? English is hard. Or if you have negatives, well, it won't be speed anymore. It'll be velocity. And it won't be distance traveled. It'll be displacement. If I'm doing donuts in my little Nissan Versa Note, if I'm doing donuts in the parking lot, I can keep it at a constant speed, and the distance travel will always be going up because I'm moving. But my velocity is going to be changing signs. Even if I'm going at a constant speed, if I'm doing donuts in my Nissan Versa Note, the velocity sometimes will be positive, sometimes will be negative. There will be an X portion and a Y portion. And at the end of the day, if I do full donuts, my displacement will be 0. I haven't gone anywhere. I've moved, but I'm still where I started. And that's what integration really gives us, displacement, net change. That's what we're going to talk about with net signed area. Now we're just going to do 2 more examples to really drive these points home. But there's really nothing new. Example 4. So again, this is a good time if you want to pause the video and start working on some homework problems, you can. If you want to see more examples, you can. If you want to take a break, you can. Try to keep the videos shorter, but especially in higher level classes, the material just gets longer. So feel free to take breaks. And again, it's always a good idea to pause the video frequently, catch up, take a moment to think, or maybe work on a problem and then see how it compares to my solution. All right, here. Part A, I'm going to have you evaluate the integral from -3 to 3, 2x dx. So we're going to do this graphically because that's really, we only have 2 ways of doing this. Like the first video with those Riemann sums, we could set up the Riemann sums. We could use the properties of the first video with summation notation, take the limit as n goes to infinity. I skipped most of that part in this section. I didn't want to do that part in this section. We only did a little bit, and it was interesting enough, I'm sure. Or we can do it graphically. And remember that the integral is the net signed area, not the total area necessarily, but we'll get into that when we get the picture. Okay, so get our graph paper out, Graph paper is optional in this class, but it's recommended to have. I think it makes things a little easier. Oh, wait, this is not going to work for a graph. We're going from -3 to 3. All right, and it's a line 2x, so it has a slope of 2, y-intercept is 0. It's going to look something like this. See, this is one nice thing about recording videos. I could never draw this straight line in class. So remember the integral. The integral is the net signed area. Okay? So the net signed area between -3 and +3 is this negative blue area and this positive, again in quotes, green area. I don't even need to calculate this out. I know the answer. This net signed area is 0. Right? Because this positive green area is the same as this negative blue area. So it's just 0. The total area is a thing. In fact, the total area, we could just move that blue triangle over. If we were looking at total area, we just add these two triangles, which is just a rectangle. That's just 3 times 6, 18. The total area is 18, but we're asked about the integral. And the integral is just the net signed area. So if I really wanted to do this out the long way, here's what I'd do. I'd say the net signed area, the integral, is this positive green area minus the blue area. And I'd say, well, the green area has a width of 3, so does the blue area, and a height of 6, so does the blue area. Area of a triangle is 1/2 base times height. And then again, we'd subtract 1/2 base times height. And that's another way of getting to the answer of 0. So that's what we're actually doing here. Taking all the positive areas and subtracting all the blue areas because we are looking at an integral, which is net signed area. Okay, so definite integrals are areas, but we treat the areas as negative when they're under the curve. All right, so next one is going to be part B. Part B asks, find the total area between, that's my shorthand for between, that's a slash, not an L. I'm not talking about BLTs here. Between F and the x-axis over the interval from 0 to 6, or f of x equals x minus 2. So again, we're going to do this graphically. So to do this graphically, we need a graph. You can use Desmos to help you, but it's really good practice to be able to do this on your own. All right, the function is x minus 2, has a slope of 1, y-intercept of -2. We're going up to 6. 1, 2, 3, 4, 5, 6. We're good. And this is what the function looks like. Now we are looking at the total area. So if it were net signed area, we'd take green and subtract blue. But it's total area. So we're just going to add blue and green together. All right, so this is a 2x2 triangle. And this is a 4x4 triangle. So the area, again, is just going to be blue plus green. So that's just going to be 1/2 base times height, because they're triangles, plus 1/2 base times height. Total area is going to be 2 plus 8. Total area is 10. The integral, if it asked us about the integral, it would be less than 10. The integral would be 6, 8 minus 2. But it wants to know total area. So it didn't ask us this, but if this were the function, then 10 would be the integral from 0 to 6 of the absolute value of this function. It didn't ask us that, but if it did, that's how we could correlate it. And you could also treat these problems as if this were if this were velocity, what's the displacement? Well, if our velocity is negative here, we're going backwards, and then our velocity is positive over here, so we're going forwards now. The amount of distance traveled in the backwards direction was the same as the amount of distance traveled in the forwards direction. So our displacement was 0. The integral is that displacement. That's a 0. Whereas over here, total area is like speed. Okay, so even if our velocity is negative, our speed is the absolute value. Our speed is positive. So this is asking how much distance did we travel? Not our displacement, but how much distance was covered. Even though we are starting by going backwards and then going forwards, we're still adding those distance covereds together. Okay, so you can think of these as velocity and speed, respectively. And that's what's going on here. There we go. Not even a 35-minute video, just areas. The big important thing, two things. Definite integral, it's just area. And specifically, we talk about two kinds of area: total area and net signed area, the latter of which is what integrals are. And you'll have to subtract negative area. I shouldn't have put quotations on subtract. You should subtract negative area. Okay? Quotations around the negative part. Let me know if you have any questions, and good luck.